We've all seen it in movies, a menacing green glow emanating from radioactive materials, capable of giving you superpowers or turning you into a villain. This popular image, while exciting, is far from reality. It reflects the deep-seated fear and misunderstanding surrounding atomic energy, a fear often rooted in misinformation. This essay aims to shed light on atomic energy, separating fact from fiction, to help you understand this powerful force. Before delving into the intricacies, let's address the elephant in the room: radiation. The word itself evokes anxiety, conjuring images of nuclear disasters and mutant creatures. But radiation is simply energy traveling in waves or particles. It's everywhere, from the sun's rays to the bananas we eat. Understanding the different types of radiation and their effects is crucial to dispelling the myths surrounding atomic energy. For instance, did you know that the human body itself is slightly radioactive? This is due to the presence of naturally occurring radioactive isotopes like carbon-14 in our tissues. We are constantly bombarded by low levels of radiation from space and the Earth, and our bodies have evolved to handle this background radiation without harm. The key to understanding radiation lies in its intensity and duration of exposure. While high doses can be harmful, low doses, like those we encounter daily, pose minimal risk. In fact, controlled radiation is used extensively in medicine for diagnosis and treatment, from X-rays to cancer therapy. To comprehend atomic energy, we must first understand atoms, the fundamental building blocks of all matter. Imagine a Lego set. Just as Lego bricks combine to create intricate structures, atoms join together to form everything we see and touch. These tiny particles, too small to be seen with the naked eye, hold the key to unlocking the universe's secrets. Atoms are composed of even smaller particles called protons, neutrons, and electrons. Protons, positively charged, reside in the atom's nucleus, while electrons, negatively charged, orbit the nucleus like planets around a sun. Neutrons, as their name suggests, carry no charge and reside within the nucleus alongside protons. The type of atom is determined by the number of protons in its nucleus, known as the atomic number. For example, hydrogen, the simplest element, has 1 proton, while carbon, the backbone of life, has 6. The arrangement of these subatomic particles dictates the element's chemical properties, influencing how it interacts with other atoms and the compounds it forms. Understanding the structure of an atom is crucial because it holds the key to atomic energy. This energy is stored within the nucleus, bound by the strong nuclear force that holds protons and neutrons together. Releasing this energy, either by splitting heavy atoms like uranium, fission, or fusing light atoms like hydrogen, fusion, is the basis of nuclear power. The nucleus, the atom's tiny heart, is where the magic of atomic energy happens. Imagine a tightly wound spring. The nucleus stores immense energy due to the forces at play within it. This energy can be released through 2 primary processes: nuclear fission and nuclear fusion. Nuclear fission, the process utilized in nuclear power plants, involves splitting a heavy atom's nucleus into lighter elements, releasing energy in the process. This splitting is typically achieved by bombarding a heavy nucleus, like uranium-235, with a neutron. The impact causes the nucleus to become unstable and split, releasing energy and more neutrons, leading to a chain reaction. Nuclear fusion, on the other hand, involves combining 2 light nuclei to form a heavier nucleus, also releasing a tremendous amount of energy. This process is what powers the sun and other stars. In the sun's core, hydrogen atoms fuse under immense pressure and temperature to form helium, releasing energy in the form of light and heat. Both fission and fusion release vast amounts of energy compared to conventional energy sources like burning coal or oil. This energy density is what makes atomic energy so appealing. A small amount of fuel can produce a significant amount of power. However, it also presents challenges in terms of controlling and harnessing this energy safely and efficiently. Furthermore, the byproducts of these reactions, particularly from fission, can be radioactive and require careful handling and disposal. This radioactive waste has become a point of contention in the debate surrounding atomic energy, raising concerns about environmental impact and long-term storage solutions. Misconceptions about atomic energy abound, fueled by sensationalized media portrayals and a lack of understanding of the underlying science. Let's debunk some of the most common myths surrounding this controversial energy source. Myth 1. Nuclear power plants can explode like atomic bombs. This is entirely false. While both involve nuclear reactions, the processes are fundamentally different. Atomic bombs rely on uncontrolled chain reactions, deliberately designed to release massive amounts of energy instantaneously. Nuclear power plants, on the other hand, operate under controlled conditions, with mechanisms in place to prevent runaway chain reactions. Myth 2. All radiation is dangerous and causes mutations. While high doses of radiation can be harmful, we are constantly exposed to low levels of natural background radiation without ill effects. Additionally, not all radiation is created equal. Different types of radiation have varying energy levels and penetrating power, influencing their potential impact on living organisms. Myth 3. Renewable energy sources can completely replace nuclear power. While the growth of renewables is crucial for a sustainable future, it's unrealistic to expect them to shoulder the entire energy demand in the near term. Nuclear power provides a reliable baseload energy source that is not weather-dependent, unlike solar and wind power. These are just a few examples of the many myths surrounding atomic energy. It's crucial to approach this topic with a critical eye, separating fear-mongering from factual information. Every source of energy comes with its own set of advantages and disadvantages. Understanding the trade-offs associated with different energy sources is crucial for making informed decisions about our energy future. Atomic energy is no exception. One of the main arguments against nuclear power is the risk of accidents, such as the Chernobyl disaster in 1986 and the Fukushima Daiichi meltdown in 2011. These events highlighted the potential for catastrophic consequences when things go wrong in nuclear facilities. While these events were tragic, it is important to note that advancements in reactor design and safety protocols have significantly reduced the likelihood of such accidents occurring again. Another concern is the disposal of radioactive waste, a byproduct of nuclear fission. These materials remain radioactive for thousands of years and require careful handling and long-term storage solutions. While advancements in waste management and the potential of reprocessing spent fuel offer solutions, the issue of long-term storage remains a significant challenge. On the other hand, nuclear power boasts significant advantages, particularly its low carbon footprint. Unlike fossil fuel power plants that release greenhouse gases into the atmosphere, nuclear power plants generate electricity without directly contributing to climate change. This makes nuclear energy a crucial player in the fight against global warming. Moreover, nuclear power plants have a high power output and are incredibly reliable, operating continuously for extended periods. This reliability makes nuclear energy a valuable asset for providing baseload power, ensuring a steady supply of electricity to meet essential needs. Atomic energy presents humanity with a double-edged sword, immense potential coupled with inherent risks. Harnessing this powerful force responsibly requires a balanced approach, acknowledging both the benefits and the challenges it poses. On the one hand, atomic energy offers a pathway to a cleaner energy future. As the world grapples with the urgent need to transition away from fossil fuels, nuclear power emerges as a viable alternative, capable of providing reliable, carbon-free electricity. Furthermore, advancements in nuclear technology, such as the development of Generation 4 reactors, hold the promise of even safer and more efficient energy production. These next-generation reactors boast enhanced safety features, reduced waste generation, and even the potential to utilize existing nuclear waste as fuel, addressing some of the main concerns associated with traditional nuclear power. However, the legacy of past nuclear accidents, the proliferation risks associated with nuclear weapons, and the unresolved issue of long-term waste disposal continue to cast a shadow over the future of atomic energy. Addressing these challenges through international cooperation, stringent safety regulations, and continued research and development is crucial for unlocking the full potential of atomic energy while mitigating its inherent risks. Fear often stems from the unknown. This rings especially true for atomic energy, a subject often shrouded in technical jargon and complex concepts. Empowering individuals with accurate information, presented in an accessible manner, is crucial for fostering informed decision-making and dispelling unfounded fears. By understanding the basic principles of atomic energy, the distinction between different types of radiation, and the realities of nuclear power plants, individuals can engage in meaningful discussions about the role of this technology in society. Knowledge empowers us to critically evaluate media reports, challenge misconceptions, and advocate for evidence-based policies. Furthermore, promoting scientific literacy goes beyond simply understanding the technical aspects of atomic energy. It's about fostering critical thinking skills, encouraging skepticism, and promoting a healthy dose of curiosity. By equipping ourselves with the tools to discern fact from fiction, we can navigate the complex world of atomic energy and make informed decisions about our energy future. Ultimately, the key to harnessing the power of atomic energy responsibly lies in striking a balance between technological advancement and societal acceptance. This requires open dialogue, transparency from the scientific community, and a commitment to engaging the public in meaningful conversations about the risks and rewards of this powerful technology. The story of atomic energy is still being written. As we stand at the crossroads of a changing climate and an ever-increasing demand for energy, the choices we make today will determine the course of our energy future. Atomic energy, with its potential for both good and ill, presents us with a unique set of challenges and opportunities. By embracing a fact-based approach, fostering scientific literacy, and engaging in open and honest dialogue, we can harness the power of this technology responsibly. The future of atomic energy is not predetermined. It hinges on our collective wisdom, our willingness to learn from past mistakes, and our commitment to shaping a future where this powerful force serves the best interests of humanity and the planet.